Hi guys, I thought I'd bring together our projectiles work and look at some of the four important formulae which might help you along your way. For a start, we're going to look at time of flight. Now if you imagine a projectile coming like this and setting off with initial speed of u at an angle of alpha, then its y coordinates or its y components at any particular time are y is equal to u sine alpha t. So I'm going to look at that u equals s equals ut plus half a t squared minus half g t squared, and really that's because g is in a negative direction and that's what makes this negative, but otherwise that's plus half a t squared. So that's where I'm going to start off, and you'll notice that if we're thinking about the time of flight, that's the time between this point and this point. So at both those points the y is equal to 0. So I'm going to say 0 is equal to u sine alpha t minus half gt squared, and if I take the common factor of t out of there, I get 0 is equal to t times u sine alpha minus half g t. So that will be one of the first things I can leave from there, is that t equals 0, and also this bracket must equal 0, so u sine alpha minus half gt must also equal 0, and from that I can say that u sine alpha is equal to a half gt, and making t the subject, I can say t is equal to, half comes up to the top times u, 2u sine alpha, and then g comes down the bottom. So the time of flight can be represented or found by just working through that. So working when y is 0, and you can just use that formula. Now you're often asked to prove these formulae, so it's worth having a good shot at them now. Right, time to the greatest height you could almost say is halfway between 0 and this point here. So it could be half of this. So t is equal to half of that, which is u sine alpha g over g. But if you hadn't worked that out already, could you work out a way of finding this formula? Well, one thing we know about this point here is that the vertical velocity is equal to 0. So Vy is equal to 0. Now if I'm going to use, let's think this time, I'm probably going to use v equals u plus at, or a version of v equals u plus at. So Vy is equal to, now my uy is u sine alpha plus at would be minus gt. Now if that's equal to 0, I've got 0 equals u sine alpha minus gt, which would mean that u sine alpha would equal gt, which means the time to the greatest height would be u sine alpha over g. So the same. This one came about from thinking, well, clearly if that's a symmetrical parabola, then time to the greatest height is half of the time of the flight. But I could always think about it from, if I was going to it from first principles, by thinking about the idea that the vertical velocity would be 0 at that point, because it comes up and then it's not going any higher or any lower, so it's got no vertical velocity at that point before it starts to come down again. Okay, so let's think about the range. Now the range is motion in this direction, so that would be this distance here. So we're looking at what's happening from time 0 to time at this point here, and that's really interesting. So when we think about our movement of x is equal to u cos alpha t. Now if I know that my t at this point is this formula here, I can say x is equal to u cos alpha times 2u sine alpha over g. Now you can see clearly I've got two u's times together. So I've got u squared, and then this combination here is 2 sine alpha cos alpha all over g. And those of you who are really hot on your trigonometrical identities would see that 2 sine alpha cos alpha is a double sine angle. So x is equal to u squared sine 2 alpha over g. So that would be an equation that would work for the range. So you can work out how far it's going to travel just from knowing the angle and the this initial velocity, which you'd hope you would be able to. Right, the Cartesian equation's a little bit trickier because I'm going to pull together these two equations. So I've got y is equal to u sine alpha t minus half g t squared, and I've got x is equal to u cos alpha t. Now when we've done Cartesian equations, when we were studying our parametric equations, we've looked to eliminate one variable. Now really the parameter within this is time, because both things based on time changing. U and alpha are constants, g is a constant, but time changes throughout. So if we can remove that parameter, that would make us much more helpful, I suppose. You'll have to see when you see the formula. But rearranging this, I get t is equal to x over u cos alpha. So substituting that into here, I've got y is equal to u sine alpha times x over u cos alpha minus half g, and then I've got this squared, so that's u squared over, so x squared over u squared cos squared alpha. Oof. Which seems a bit of a mouthful. Now looking here, I can clearly see that those u's cancel, and I've got sine alpha over cos alpha, which I think you'd recognise would be tan alpha. So y is equal to x tan alpha. Tidying this up here, I've got g and x squared on one level and 2 and u squared on another level. Then here I've got cos squared alpha on the bottom, or 1 over cos squared alpha, which is sec squared alpha. And I suppose that works as a final thing, but we can go just a little bit further by thinking, well, maybe if this is in terms of tan, it would be nicer to have that in terms of tan. So I could say y is equal to x tan alpha minus gx squared over 2 u squared. And our sec squared is 1 plus tan squared alpha. So, what that means is, knowing the starting point in terms of the angle and the initial speed, and knowing how far it's travelled lengthways, I can now work out how high it will be at that particular point. So this is my Cartesian equation, which is quite a handful, but always useful to know. I think these will speed you up in all sorts of little bits and bobs of questions. This is aiming for a very specific type question, which you'll come across when you do the exercise. But you will be asked to prove these, so always think about how I got to them by first principles. Okay.